All right, we have one that is structured in a very bizarre way, and I think it's obvious what we don't know off the top of our head, and that's delta x. Normally there's an extra little factor hanging around here on the end, and we're like, oh, look, I found my delta x. There's an n in the denominator, yay. And sometimes, yeah, and this time, no. And actually, on all the ones that we have done before, with the exception of the last one, we had only one possible answer. There are actually an infinite number of things we could do on each of them, but for the first two, we did one answer. For the previous one, we did two possible answers. For this, there's again, infinite number of them. We're only going to do one possible answer, depending on what we say that delta x is. And I'm going to restructure this just a little bit. I'm going to just start rewriting the whole thing. And I'm tempted, for the sake of time, for the sake of ink, to just be like, oh, I just want to restructure this. Let's ignore that. This is part of it. We may not be talking much about this, but this is part of it. So mathematically, it is part of the operation of what we're doing. We're taking a limit. We're adding stuff together. It has to come with us. And it was worth me spending 30 seconds talking about that. Now you're going to go back in the video and see exactly how long I spent. And that should not say infinity. It should say n. Now I have to start the whole video over. Okay, let's restructure this, and I'm going to restructure it to where delta x is a little more obvious. How do you know what delta x is? You don't. Just put an n in the denominator and go with it. So, there. Let's do that. We'll start there. And that means that we have done that, which means that I could, well, I need a k in here for sure. I need a k. So now we really just have to figure out where that pi goes. And you can put the pie anywhere you want. You can put it on your dessert plate if you like. Sorry, that was bad. But I'm going to just put the pie in here, which technically means it should go in front of the k. I'm going to put the pie in front of the k right there. And that means that this is a 1. What if I want to put the pie here? Then you're not wrong. You might be complicating your interval a little bit, but you're not wrong. It'll totally work. Trust me. So based on what we have structured this to be, we would have a width of 1. Okay, so width is 1. Now, again, if you want to put the pi over here, then the width would be pi, and you would have explored a different possible answer. You could, let's get crazy, you could put the square root of pi here and the square root of pi here, and you'd have yet another possible answer. You could have 2 pi here and 1/2 pi here. And no, actually, you could have 2 pi here and 1/2 in the numerator there. And there's all kinds, infinite number of things you can do. You'll get the same answer. They're all crazy complicated, except I think this one is the easiest one. So this means that b minus a is 1, which means my integral answer, ooh, that wasn't squeaky that time. My integral answer is going to have a width of 1, so it starts somewhere and it ends 1 unit later. And dx, because that's part of the operation. Don't panic about what that means. We'll deal with it. Not today. Well, not in this video. So let's see. If we're going to structure this like that, then we have to realize what we're truly dealing with. So I'm going to erase a little here just so I don't have to write the whole thing all over again. It did say pi times k over n, so I'm just kind of keeping this in mind. And I really want it to be like k times the width of my rectangles, which is 1 over n. So I need a 1 over n here, which means I need a k here, and I need a pi here. That's the same thing as what I had, okay? So same thing, which means, last 3 examples have been like this, which means a is 0. So what am I doing to my input? Well, I'm multiplying it by pi. I think that's the biggest question. So if you have questions about how do I know what my input is, you ask yourself, what am I doing to my input? Top of the paper on the back, you're cosigning your input. What are you doing to your input on the second problem? You are multiplying it by 2 and adding 1, and that 1 is not where you start, okay? In this one, you're multiplying it by pi. That's what you're doing, okay? So the function itself is pi times x in this case, and we actually have this, which corresponds to this, which means a is 0. So we start at 0, we end 1 unit later. So left-hand sum, I call it left-hand sum, also a left Riemann sum. So left Riemann sum and a right Riemann sum. You know what to do here. You can take the original, set this to 0, and you're good to go. Totally fine. I'll use red this time. The limit as n approaches infinity. We've been through this. K equals 0 to n. That means that we are going to start counting our rectangles at the leftmost portion of the interval, which means we would have 0 rectangles as we begin. And then pi times k over n squared. Yes, that would make that 0 for the very first one. Or, again, equals. Oops, I left off my limit. Let's try this again. Or the limit as n approaches infinity of k equals 1 to n. Same thing, we're just resetting it back one. I know you've seen this over and over, but the more you see it, the more you know it. There we go. I'm pressing the wrong button, and it's not stopping. Oh well. Well, as I was pressing the wrong button and it wasn't stopping, I was standing here thinking, well, what should I do? Should I go into this explanation of what's on the bottom of the paper? And yes, I will. So now that the video did not stop, I'll do that very quickly. At the bottom of the paper, if you wanted, yes, feel free to follow along with this. If you wanted to know how to find an infinite sum, a sum with an infinite number of rectangles, you would follow this through. But what we haven't done is actually compute it. So on the front of the paper where it said, now find the exact area, we used a trapezoid. Well, what if it wasn't a trapezoid? There are different formulas we could use for that, like if it was linear, if it was quadratic, if it was a constant. There's a lot of different things. Used to have students memorize those things. They're not very necessary, so we're not going to do that. I realize that that is not nearly as tested as I thought it was. So if you are interested, and after this, if I can get this the stop button to work, if you are interested, if you deeply care, you can glance down here at the bottom and you can see how we get an exact answer of what we got on the front, which was 24. When we found the exact, this is my scratch work, the exact answer of 24. That can happen with an infinite number of rectangles with a left or a right-hand sum. There's going to be some steps in here that pull out some very obscure formulas that I have not mentioned, but it does work.